Good morning all. Here's a fun circuit that you can put together based around the Arduino Uno right here and this ping sensor. Now the ping sensor is fascinating, a lot of fun to play with. I have on pins 9 and 10 of the Arduino Uno an LED connected to pin 9 and a buzzer connected to pin 10. The output, the signal output of the ping sensor goes to pin 7. Now this is a prototyping board. Let me take this off right here. I'll set the Arduino out of the way. But this right here is a prototyping board that mounts on top of the Arduino Uno. And you can put anything you want on this little board right here. There's my wiring to wire the ping sensor, the LED, the current limiting resistor, and the buzzer right here to the stake pins. The stake pins fit down on these connectors right here. Now, the nice thing about the Arduino Uno is you can download the programming IDE, Interface Development Environment, and you can program this Atmega IC right here through the USB port. And another nice thing, that makes it very easy. They have their own development environment. But the main thing I believe that makes this system cool is in that IDE they have example programs for all kinds of different types of sensors. They have one for this ping sensor. They have they're called sketches. They have sketches for temperature sensors, light sensors, all kinds of different sketches pre-set up for you to add your code to, but they get you up and going really quick. Let's set this back up on top of the Arduino Uno. Now they also have, I have one at the house, Arduino Mega, and that has more inputs and outputs and more functionality. But for simple circuits like this, and even for complex circuits, this Arduino Uno is very nice. Now I took their sketch and I added my code to their sketch to turn this LED on and off, turn this buzzer on and off based upon the distance an object is from the ping sensor. So when I'm close to the ping sensor, within 6 inches, this rapidly blinks. And as I move away from the ping sensor, the LED blink, turning on and off, and the buzzer buzzing on and off starts to slow down. And past 3 feet, it no longer blinks and beeps. Let me plug the battery pack in here. I got a little battery pack. There's a DC voltage input right here on this connector. And so I'm going to plug this in. And you can see it rapidly blink and buzz. Let me move my hand away. There it starts to slow down in frequency. And that's the slowest frequency. That's right on the edge that I have it programmed to see an object. Now I'm outside, farther up in the air. And I'm outside the range. Let me come back in. Isn't that fascinating? What a simple circuit. Well, it's not simple, but the functionality is simple. Now you could have, for instance, an analog output going to a speed reference of a drive, and based on the distance an object is away from that ping sensor, your analog speed reference could slow down if it's real close to an object, or speed up, increase the analog voltage when it's farther away. Or you could have it turn left and right. You could have like a servo motor, and one output would make it go left if it's close to an object, and another output could make it go right if it's close to an object, and if there's no object in front of it, it'd go straight. All kinds of different things. You could attach this to your robot. Multiple analog inputs, analog outputs, digital inputs, and digital outputs on that Arduino Uno board. Very nice. Now, I'm going to connect pin 7 of the Arduino Uno. That's the signal out of the ping sensor. It's actually bidirectional. There's a request in to take a measurement, and then there's a signal back to the same pin. You'll see that on the scope. I'll point that out. So pin 7 is the signal into that Arduino Uno from the ping sensor. I'm going to connect the scope's ground to the ground of the ping sensor. That's the easiest way I can get on the ground. Give me a little bit to get that scope hooked up to it, and we'll look at the waveforms of pin 7, the signal out of that ping sensor. Alright, I'm going to plug the battery pack in, and we'll see what we get on the oscilloscope. You can see it. I'm going to spread the time out a little bit, but you can see the request. Right here, there's a low, then a high to low pulse that starts that transducer to look for an object. And right now, it's looking at the ceiling. So if we were to divide this in half, that would be the time it takes for the ping to send a chirp. And then the chirp is received, it bounces off that object into the receiver. So here, if we divide that time in half, that's the distance to the ceiling. Okay, let me set this up to look and see. Let's go to vertical bars. Let's dial that in a little bit. Let me go to the leading edge. We're going to get the total time with this measuring device right here. Okay, it says we have, between the leading edge and the trailing edge, we have 10.8 milliseconds in time. I'm going to put that into the calculator. Oh, I got in front of the sensor. I'm going to put that into the calculator. Try to do this around the camera. Okay, here's 10.8 milliseconds divided by 74 microseconds equals 145.95 inches. Now we divide that by 2, and we have 72.97 inches. We'll divide that by 12 to get feet. And from the top of my bench to the ceiling is 6.08 feet. Now I'll explain the 74 microseconds when we take a look at the code. They have good explanations in the remarks of their example sketch for that ping sensor. Now, watch what happens when I get close. Okay, I'm gonna reset this time here. Let's get rid of the cursors. Take that menu away. Let's go to the horizontal menu, and we'll set this to 50%. So now it triggers at 50%. Is that right? Is it set to 50? Yes. Okay, and I'm going to move that position over a little bit. Let's get recentered. And I'm going to spread the time out. Here's the leading edge of the chirp. Now, let's change our scale. See what that does. There it is. You see how when I get farther away, that send and receive signal gets wider and shorter. I'm close to the sensor. I'm moving farther away from the sensor. Okay, we lost it. Isn't that amazing? Let me come around the other side of the camera. If I get too far away, we lose the trigger. Okay, I'll show you the code, I'll show you the sketch. Arduino calls them sketches when I get back to the house. Here we are at the house, and we're going to talk about the sketch that interfaced to the ping sensor. Now let me go over here and show you where you can find the base program for the ping. You go down here, Files, Examples, over here, Sensors, and Ping. And when you click on that, it will open up a sketch that will allow your ping sensor to work. And you can add your code to this base program. Here is the code for the ping sensor. This sketch reads a ping ultrasonic rangefinder and returns the distance to the closest object in range. To do this, it sends a pulse to the sensor to initiate a reading, then listens for a pulse to return. The length of the returning pulse is proportional to the distance of the object from the sensor. The circuit is connected in this manner. You have a plus V pin that's connected to 5 volts. You have a ground pin connected to the ground of that power supply. And you have a signal connection of the ping. And it is attached to the Arduino Uno on pin 7. Now these folks right here, these two folks wrote this code to interface and allow the function of this ping sensor. These are two geniuses. David A. Mellis created the original code on the 3rd of November 2008. Tom Igu, he modified the code 30 August of 2011. This example code is in the public domain. Now, if you want to see a tutorial on the ping sensor, you can go to this address right here. Click on this link right here and it'll take you to a website that shows you how that sensor works. The first thing we have to do with code is to set up the constant integers. We have the ping pin that connects to the signal pin of the sensor, the ping sensor, and that goes to pin 7. This constant won't change. It's the pin number of the sensor's output. Then we have constant integer LED 9. LED equals 9, and that is the pin 9, where the LED circuit is connected. That allows us to turn that LED on and off from the Arduino, pin 9. We have the buzzer on pin 10, constant integer buzzer equals 10. And the Arduino turns the buzzer on and off by turning pin 10 to plus 5 volts or ground, 0 volts, plus 5 and 0 volts. Constant integer threshold equals 12. This is an arbitrary threshold level that is within the distance range of the ultrasonic distance center. I've got it set to 12 inches. You could set that to anything you wanted to. The threshold is the comparison value that we are looking at to determine that it's set to 12 inches. Here we have to initialize the serial communications, the LED and the buzzer. The serial communications .begin sets the baud rate to 9600 baud. Now we want to set the LED and the buzzer to outputs. So we go pin mode in parentheses LED comma output parentheses colon. That tells that pin 9, where the LED circuit is attached, that pin 9 is an output. Pin mode buzzer comma output, that tells us that sets up the program so that pin 10 of the Arduino will turn that buzzer on and off. And this is in a void setup loop. Brackets, beginning bracket, closing bracket. We have another void loop. We want to set the duration variable, the inches variable, the centimeters variable to a long numeric value. That sets these as long variables. In this part of the program, we want to trigger the ping sensor. That was that very short, brief, low to high to low pulse that you saw in the video. The ping is triggered by a high pulse of 2 or more microseconds. Then give a short low pulse beforehand to ensure a clean high pulse. So pin mode, ping pin, that's pin 7, set it to an output. Digital write ping pin, low, we start out low, we have a delay of 2 microseconds. Now we have a digital write on pin 7, high, so it goes to plus 5 volts. We have that delay of 5 microseconds. And then we digital write ping pin, that's pin 7, low. So we have a low to high to low with a width of 5 microseconds. The same pin, that ping pin, pin 7, is used to read the signal from the ping sensor. A high pulse whose duration is the time in microseconds from the sending of the ping to the reception of its echo off of an object. So now we have to convert pin 7 from an output to an input. So we go pin mode, parentheses, ping pin, comma, input. Now the duration, the variable duration equals the pulse in, parentheses, ping pin, comma, high. So as long as that input now, ping pin on pin 7 is an input, as long as it is high, we are going to set the duration according to the time that that pin is high. Here are two what I call subroutines. I'm not really sure. I guess you could call them functions. We have a function called inches equals microseconds to inches, comma, duration, the time that that input was high on pin 7. And we have centimeters equals microseconds to centimeters based upon that duration that the input pin, pin 7, was high. Let me go down here. While we're on this, let me go down here and we're going to look at those functions. We have a long variable again called microseconds to inches. Long microseconds. Now, according to Parallax's datasheet for the ping sensor, there are 73.746 microseconds per inch as sound travels at 1,130 feet per second. This gives the distance traveled by the ping, output, and return. So we divide by 2 to get the distance of the obstacle. And another tutorial on the ping sensor given right here. You click on that link right there and it'll give you more information. So when returning from this subroutine, we have the microseconds, this variable up here, divided by 74, that's our 73.746 microseconds per inch, rounded up to 74, and then divided by 2 because you have the chirp out and the echo back. You only want the distance to the object, not both distances out and back, so you again divide by 2. Down here for the centimeters, you have long microseconds to centimeters, and here's our microseconds variable that is returned. The speed of sound is 340 milliseconds or 29 microseconds per centimeter. The ping travels out and back, so to find the distance of the object, we take half of the distance traveled. And that's returned from this function. Microseconds divided by 29, that's our 29 microseconds up here, and divided by 2 so that we have only the return signal in microseconds. Let's go back up here. Here we have, you remember we set up the baud rate at 9600 baud. Well, you can go and look at the actual inches, centimeters, and I added this right here, the duration from the Arduino through the USB and converted to RS-232. Let's do that real quick. I'll bring that up. You go to Tools, go to Serial Monitor, and it should pop up in just a little bit. Where are we at now? Try it again. I don't see it. Oh, let me go down here and click on this. There it is. Okay, here we are. Let me close this. And we'll start again. Serial monitor. There we go. There's our Arduino. Now right now it sees the ceiling from my computer bench top up to the ceiling is 65 inches, 166 centimeters, and the duration is 96,000 thereabouts. I got my hand over the ping sensor, and we got 1 inch distance between my hand and the ping sensor. Let me move up a little bit. There we're past 6 inches, less than 12. There we're past 12 inches. Can you hear the beeping? Notice it gets slower as I get away from the ping sensor. Let's go take a look at that code. Now, if inches, we're here in America, we use inches, feet, and miles. If inches is less than threshold, remember that threshold was 12. So if inches is less than threshold divided by 2, that gives us 6 inches. Then digital write, LED, that's the LED on pin 9, we set that high so it turns on. And digital write, the buzzer, which is on pin 10 of the Arduino, we set that high so it beeps. And we have a very fast delay here, not long at all. If I set this to 1000, you'll see it in a little bit. If I had set this to 1000, we'd have a delay of 1 second. So this is a fairly high frequency. Not so high that you can't hear the beep and the LED turn on, but high enough so that you can tell the difference. We have, after the delay, we have a digital write of LED low that turns that LED off on pin 9. We have a digital write of buzzer, comma low, and that turns the buzzer off. And then we have another delay. And as long as we're within 6 inches, that's threshold divided by 2, 12 divided by 2, this if statement will continue to activate. We go down here to a else if. Now if inches is greater than or equal to the threshold divided by 2, so if we're greater than 12 divided by 2, which is 6 inches, greater than or equal than 6 inches, and less than 12 and inches is less than or equal to 12, we perform this if statement, this else if statement. And here you'll notice it's exactly like the above statement, but we increased the delay time to 100. And that LED and buzzer turned on and off at a lower rate, a lower frequency. Now we'll go down here, and else if the inches are greater than or equal to 12 and inches is less than or equal to 12 times 2, which would be 2 feet, we perform the same function but with a longer delay, so that the beep and LED turning on is again at a slower frequency, and 500 is a half a second. Now here we get to a delay of 1 second. Else if inches is greater than or equal to 12 inches times 2 and inches is less than or equal to threshold times 3, that would be between 2 feet and 3 feet, we have the LED and buzzer turn on and off at a 1 second rate. Now finally, if we're beyond that 3 feet, the final threshold times 3, or if the window or the ping sensor is not seeing an object, else digital right LED low and digital right buzzer low, both being turned off. Isn't that fascinating? I tell you what, the folks that put these things together, they are amazing. Let me go back to the serial monitor. That's fun to play with. Y'all go out there and make that. Go out there and make that circuit. You can find these sketches that get you started under File, Example. Look at all those things you can play with. Amazing. Amazing. All right, all. Hope you enjoyed that. Hope you and your families are doing well. We'll see you next time. It's a little circuit to watch my back. Sees the camera.